Thank you for joining us for this broadcast of Science and the Solar Eclipse. I'm your host, Gordon Dickson. We are continuing our discussion of the connections to the solar eclipse and what we have learned about science and what science has taught us as a direct result of solar eclipses. And with us again today is Dr. George Matzko. Dr. Matzko, thank you very much for joining us.
Thank you. I've enjoyed it.
We talked last time about what we learned about the topography of the moon as a result of solar eclipses, and we didn't mention Bailey's beads, but that comes out every once in a while. What are Bailey's beads in a solar eclipse?
So as the moon covers the sun during a solar eclipse, the rugged topography of the lunar limb allows beads of sunlight to shine through in some places, while not in others, valleys and that type of canyons and, craters and that type of thing. So these are named for Francis Bailey, who explained the effect in 1836. And sometimes they call it the diamond ring, I understand, or sometimes even a double diamond ring, depending on which part of the moon the sun is shining through.
And one of the connections we made in the last broadcast is we've learned so much about the sun and its composition, the stars and their composition, and even the moon. We've learned so much about it, but we've also learned a great deal about light and understanding Einstein's proposal that gravity would affect light. And you mentioned last time this was actually proven by Arthur Eddington in 1919. I think as a result, Einstein actually won the Nobel Prize. Talk to us about the implications of gravity affecting light. How does that work, and what has that taught us about the universe around us?
This idea about gravity being just the bending of space-time really just changes our whole way of thinking about the universe. When we think of massive objects like the sun bending the paths of light rays, passing near them, deflecting them from the straight line trajectory, we call this gravitational lensing. And we still use gravitational lensing today. Perhaps our listeners have heard about the James Webb Space Telescope. Mm-hmm. And it can see really far into space, further than we've ever been able to see before. But it actually can see even further using this effect of gravitational lensing. In other words, they will train the James Webb Space Telescope on these massive galaxies that we see even in the early universe. And because of the great mass of this body of stars, it'll actually bend the light around this mass of stars and acts like a lens, like a magnifying lens. And we can actually see stars and galaxies beyond the natural limit of this James Webb Space Telescope. So it's allowed us to see further than we could have ever seen before.
And so just that one concept that may not be very familiar to our listeners of how is it even possible, or what does it really mean that gravity has an influence on light? How does that affect our understanding of, you've referred to the curvature of the universe?
So when we're talking about the path of light, light's going to follow a straight line. But what is a straight line through curved space? So a straight line through curved space is not, straight with a ruler. It actually curves with the curvature of space. So I think about it this way. I was teaching refraction to my students in physics one time, and we were talking about how light bends when it goes through different medium, and we have the index of refraction and so forth. And I said, if you're a lifeguard and someone is out drowning in the ocean, you need to rescue them. The fastest way to get to that person drowning is not to run in a straight line from the lifeguard stand to where they are drowning. Mm-hmm. The fastest way might be to run up the beach and then go into the water, because we can move a lot faster on the sand than we can wading in the water or swimming in the water. And so it depends on the medium through which we're going. So maybe that analogy will help people understand that a straight line is not necessarily the quickest distance, the fastest distance between 2 points. Mm-hmm. So as space-time is curved, the light bends with it as well. So maybe it's not right to say that gravity is bending the light. It's better probably to say that the mass of the sun is bending space-time, and that's causing the light to bend. And that effect that we see of the bending is actually what we call gravity. Mm-hmm. We used to think of gravity as a force, but now we don't think it's a force anymore. I mean, all forces we know of are usually, there's something causing the force, some kind of exchange particle that's taking place that's causing the force. But we've never found anything like a graviton, mm-hmm. okay, that would cause a force between two objects. And so it looks like gravity is not a force after all. It's actually just this effect of a mass or energy curving space-time, and light going in a straight line, at least the quickest distance from one point to another.
And I suppose this is the reason that people have not been able to explain gravity right here on Earth. I mean, right for us at this very moment. The understanding of gravity, if I understand it correctly, has so far eluded us.
Yes, it's interesting how we often in science talk about things we don't understand. Mm-hmm. I mean, if I say the word gravity with enough confidence, people think I know what I'm talking about, especially if I wear a white coat. But the truth of the matter is that we really don't understand what gravity is, unless it is this curvature of space-time. And that's really hard to conceive of.
I know that in 1919, when they made those observations, which confirmed what Einstein had said, there were some objections, and a colleague of Eddington, Frank Dyson, actually responded to some of those objections.
Right. So Dyson was concerned about potential errors in the measurement of star positions made during the eclipse. He questioned the accuracy of the photographic plates used to capture the position of the stars near the eclipsed sun, which showed the shifting, the curvature of space by the sun. To answer this objection, Eddington and his team carefully analyzed the photographic plates, took precautions to minimize errors in the measurement. They also compared the results with previous observations under different conditions to ensure consistency. You know, it's interesting to me. I was talking to someone at a church who didn't believe in general relativity, and he was saying that the observations by Arthur Eddington in 1919 didn't prove Einstein's theory of general relativity because the measurements are so crude. And I said, well, that may be the case, you know, strictly speaking, but there have been many, many other observations later on, other eclipses and so forth, and the equipment was a lot better. So to hold up, you know, those shortcomings as far as measurement errors are concerned, as falsifying Einstein's theory of general relativity, I thought was disingenuous. Mm-hmm. Dyson also talked about systematic biases. He was concerned about systematic biases in data that could lead to incorrect conclusions. He suggested that factors such as atmospheric turbulence, instrumental effects, selection biases could influence the observed positions of stars. Eddington and his team addressed this objection by meticulously analyzing the data and accounting for potential sources of bias. Mm-hmm. They also conducted statistical tests to assess the reliability of their measurements and conclusions. Dyson proposed alternative explanations for the observed deflection of starlight unrelated to Einstein's theory of general relativity. He suggested the apparent displacement of stars near the sun could be due to unknown atmospheric effects or variation in the Earth's gravitational field. But Eddington and his team, I think, successfully argued that these alternative explanations were less plausible and failed to account for the precise measurements observed during the eclipse. Mm-hmm. They also emphasized consistency of the results with Einstein's theoretical predictions. Dyson also expressed concerns about confirmation bias, suggesting that Eddington and his team may have been influenced by their preconceived beliefs in Einstein's theory. To address this objection, Eddington and his team adopted rigorous scientific methods, openly debated their findings with other scientists. They also encouraged independent verification of the results by astronomers around the world. So in the end, despite these objections, Eddington's findings from the 1919 solar eclipse observations provided strong experimental support for Einstein's theory of general relativity. And over time, subsequent observations and experiments further confirmed the predictions of general relativity, solidifying its status as one of the most successful and influential theories in modern physics.
I remember in that paper that someone actually raised the question as to whether or not the heliosphere or the atmosphere of the sun was actually influencing that starlight. And I think it was in that paper they mentioned that they have photographs of comets that were closer to the sun than the direct rays of that starlight, and that those comets were unaffected. So it wasn't because of something in an atmosphere or heliosphere around the sun that was doing it either. And as you say, I think just as 3 years later, I think it was Campbell and Trumpler who reconfirmed it in watching an eclipse in Australia.
Really hard to overthrow an accepted theory. For example, the Newtonian idea of gravity being a force. And, people resist that. And scientists are just people, and they resist, a change in paradigms. And that's just the way science works. Eventually, the evidence builds up, and finally, the old paradigm crumbles. I think it's interesting, though, that in our day, that we still teach children the idea of gravity being a force, even though we're aware that it's not. And it's almost like, they're too young to understand the truth or something. Mm-hmm. And I think that's unfortunate.
Mm-hmm. Mm-hmm. This really gets us into a very interesting area, which I would imagine would be new to a lot of our listeners. So we'd like to come back and talk about this just a little bit more, especially if light has no resting mass, how it is actually affected. And so how can we further describe that to the limits of what we understand at this time? Thank you again for a really interesting and fascinating discussion about this entire area, and we'll talk again soon. Dr. Matzko, thank you very much for joining us today.
Thank you for having me.
Thank you again for joining us for these series of conversations with Dr. George Matzko. He can be reached at his website, georgematzko.com. That's GeorgeMatzko.com. The Matzko Science Ambassadors. These broadcasts are brought to you by LiveServeLead.com. Live, Serve, Lead, helping others succeed.